In the last lecture, we studied the basics of vectors. We defined the basic operations on vectors like cross and dot products, and then we saw the differential operation on vector. So, we introduce this differential parameter, which is a vector operator called del, which is defined as this, and by using this operator then we define three operations on vector: the del of f, where f is a scalar quantity, and del of f gives you what is called the gradient of the scalar quantity f. So, this is del of f is a vector quantity, and physically we saw it tells you the maximum rate of change of this function f in the 3-dimensional space. Then we defined for the vector fields the operations, which was the operation del dot f, and this quantity we call as the divergence of vector f. This quantity is a scalar quantity. Thirdly, we had defined the vector operation, which was the cross operation, and we call that as the curl of vector f. So, del cross f is given as a determinant of this matrix. In this lecture today, we will try to get a physical feel for these operations, the divergence and the curl operations, and we define then the basic theorems which are used in the vector operations. So, just to get a feel for the dot product, essentially if you consider the vector field like a fluid, consider a small box or small volume and ask how much is the net flow of the fluid from that box per unit volume. That quantity is nothing but the divergence of the vector. So, if you imagine the vector field something like a fluid, then the net flow which will be coming out of the volume per unit volume will be essentially represented by this, which is the divergence of the vector. Similarly, when we look at the curl of the vector, as the name suggests, it is something curling or there is something rotation is involved here. So, if you consider a vector field and keep an object in that and treat a vector field like, let us say again, like a fluid flow or something, surface of a river, and try to keep some object on the surface of a river, because of the differential flow of the layers of the water, there will be some kind of a rotational effect which will be created on the surface of the river. That is the effect which is captured by this operator, what is called the curl operator. So, if we define the net rotation created on an object per unit area of the object, then that quantity essentially is the curl of that vector field. So, just to get a little better feel, let us ask what kind of fields would give me the divergence and what kind of fields will give me the curl. So, if I draw, let us say, a vector field which is given by that, again we are writing the arrows which are representing the vectors. So, if I consider a vector field like this, that means if I consider the magnitude of the vector here, 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 they are same. It is here, here, here is same, here, here, here is same. But if I move in this direction, this value is same, but this value is different, and so on. Now, imagine if I keep a small area here, then depending upon the value of the vector, it will create some kind of a shear on this object. So, this vector will try to rotate the object this way, whereas this vector will try to rotate the object in the anticlockwise direction. So, there is a net rotational effect which is created in this object. So, if I have a vector field something like this, then I will have a rotation created, and this vector field will have a curl in this region. If I consider a field which is like that, That means now the field magnitude is changing in this direction. So, here we have certain value of the vector increases and so on. If I consider now a small volume in this region, and if I treat this vector like a fluid, it will represent the fluid which is going inside is having the value which is this, whereas the fluid which is coming out of this will be having a magnitude which is much larger. So, then it will give me a net flow of fluid from this volume if I keep some volume at this point. So, if I have field something like this, then it will have a divergence. If I have something like this, then it will have a curl. So, whenever we have some kind of a flux coming out of a volume, then the concept of divergence is the correct concept. It can capture that effect of something oozing out of that volume or getting inside that volume. If I have a physical phenomena where some rotation kind of effects are involved, then the phenomena which can capture that effect is the curl. So, divergence and curl essentially are the mathematical operations which capture this phenomena. So, you will see later on when we go to the general analysis of electric and magnetic fields, essentially the concepts of physics are mathematically captured by the curl and divergence operations. The another operation which is defined in terms of the del or this differential operator is what is called the Laplacian operator. This is actually a second order differential operator, and this is denoted by del square, which is equivalent to say del dot del. So, if I treat the del like a vector, then the dot product of this del vector is the operator del square. So, this operator, Laplacian operator, is a scalar operator, and therefore, this is, if I take a dot product of the del operator, and if I treat this like a vector, I will get the dot product of del with itself. So, this will become d2 by dx square. So, this is d2 by dx square plus d2 by dy square plus d2 by d z square. So, the Laplacian operator is a second order differential operator, and this operator is a scalar operator. If I operate this on a scalar quantity, the Laplacian operator will be del dot del of the scalar quantity. So, for a scalar function f, the del square operator, del square of f will be equal to del dot del of f. Since we have defined this quantity del of f as the gradient of the scalar function f, and this dot represents the dot product or the divergence, the Laplacian of a scalar quantity is nothing but the divergence of the gradient of the scalar function. So, this Laplacian operator in this case is divergence of gradient of the scalar function. The del square operator, however, is not restricted to the scalar functions only. The del square operator can operate also on the vectors, and if I follow the same thing as we have done here, that del dot del, and if I put a vector in front of it, I will get del dot del of the vector f, capital F, but that will not have any meaning because we have not defined the operation del of a vector quantity. When the del operates on a vector quantity, it can operate either as a divergence or as a curl. So, in this case, when we operate this one on the vector quantity, we directly take this and operate this on directly on the vector quantity. So, when we have a Laplacian of a vector, vector f, then del square of f, where f is a vector quantity, that is equal to operating this on all the 3 components of vector. So, essentially you take the second derivative d2 by dx square of the entire vector, which is 3 components. You take second derivative with respect to y of the entire vector, and you take second derivative with respect to z for the entire vector. So, in this case, although the del square operator is a scalar quantity, that operator is a scalar operator, when it operates on a vector, you get a quantity which will be a vector quantity. So, when the del square operates on a scalar quantity, you get a scalar function. When you operate this on a vector quantity, you get a vector quantity. So, in this case, you will get d2 by dx square f plus d2 by dy square f plus d2 by dz square f. What that means is that if I expand f in its components fx, fy, fz, you will have the d2 by dx square for all the 3 components, d2 by dy square for all 3 components, and d2 by dz square for all the 3 components. So, if I expand this and if I say the f is f of x into x plus f of y, y plus f of z, z, then I can substitute into this. So, del square of f will be equal to d2 by dx square into f of x, x plus f of y, y plus f of z, z plus d2 by dy square, same thing, plus and so on. Then I can combine the x component in all the components. So, that will give me d2 fx by dx square, d2 fx by dy square, d2 fx by dz square, that will be the x component of this vector. So, this will be d2 fx by dx square plus d2 fx by dy square plus d2 fx by dz square, that will be the x component, plus similarly will be y component and so on. So, essentially I take this Laplacian operator which is operating on each of the components. So, this I can say this is equivalent to saying this is del square of fx into x plus del square fy into y plus del square fz into z. So, if I take each of the components of the vector, make the scalar Laplacian operation on each of the components and write the final vector, that will be the quantity which will be del square f, where f is a vector quantity. So, later on when we do the analysis of the vector fields, you will see this operation will be needed, right, for solving the electromagnetics problems. These are the differential operators, and then we have to do the operation which are the integration of the vector fields. So, we require certain operation which we can do in the integration kind of operation. So, if I have a vector field, there is a possibility that I can take the integral of this vector field in a plane along a contour or along a line. So, it is possible I have certain vector fields and I can take the integration around a path, a contour. It is possible I can take the integration of this vector on a surface which could be a closed surface or open surface. So, I can have something like that is a surface. I will require the vector field is something like this. Here again the vector field could be like that. So, I will require the integration of this vector along this path. I may get the integration of the vector on this surface, or I can take the integration over the volume if the surface is a closed surface. So, now when we do the integration, if the integration is done along this path, we call this as the contour integration. If I take the integration over a surface, we call that as a surface integral, and since surface is a two-dimensional thing, essentially we will have a double integral for the surface integration. The contour integration is a single integration, and if I go to a volume integration, then it will be a triple integral, right, in the three-dimensional space. Then we have important theorems which connect the line integral to the surface integral and surface integral to the volume integral. So, if I have a volume here, I will have the integration over the volume. So, I have here line integral, I have surface integral, and I have volume integral. And invariably we need to change from one integration to another. We may have to convert from the line integral to the surface integral, or from surface integral to the volume integral. It should be kept in mind, however, that the integral is a scalar quantity. So, when we do the line integration, the final answer will be a scalar quantity. When we do the surface integration, the final answer will be a scalar quantity. So, now we can define the surface integration and the volume integration and the line integration as if I take some vector A, some vector field, let us say denoted by A is my vector field, then the line integration around a path of contour, some contour C, is integral A dot dl, where dl is the segment along the length. So, this quantity is dl, and this is the direction of the segment. If I am integrating along the contour like this, so dl is a vector quantity because it has a length and it has a direction. If the contour is a closed contour, then I will have the integral which will be the closed integral. So, here this is open integral, open contour. If the contour is closed, then the integral will be denoted by this. So, E dot dl, this is closed contour. So, at every location essentially what we are doing is we have this vector A, we find out the dot product of A and dl at every location, you add up that along the contour, and that is this line integral. So, this is the line integral. We can do the similar operation for the surface integration. So, let us say we have some surface like this, and there is an infinitesimal area on this which is given by dA. This is the direction of that area, this is the unit vector in the direction perpendicular to that infinitesimally small area, and the vector field is again A. So, I can define the surface integration, again the surface may be closed, it may be open. So, here this vector and the area which is a vector quantity. So, this is the infinitesimally small area, and the direction of the area is the direction which is perpendicular to this area. So, dA vector area is the infinitesimally small area and the multiplied by the unit vector which is in the direction perpendicular to this area. So, if I take the dot product of these two A and dA, and if I sum up over the entire surface, that gives me what is called the surface integral. So, we have here now surface integral. So, if I have surface which is the open surface, then I have this as double integral A dot dA. This is for open surface, and A dot dA for the closed surface. So, the integration now is a double integration because we are talking about a surface, and if you write the integration like this, then it represents the open surface. If you write a loop around the integration, then that represents the integration around the closed surface. Again, you can note here we are taking a dot product of the vector A and the area at that location. So, this quantity is a scalar quantity. So, this integration is going to be a scalar quantity. Now, direction of the normal which we take for A, if it is a closed surface, then the direction of normal generally is taken as the outwards normal from that volume. That direction is taken as the positive unit direction. However, if you consider a surface which is the open surface, then of course there is no preference for defining the unit normal. So, we can define the unit normal in either direction. So, if I consider a surface which is like this, the unit normal can be defined either this way or it can be defined either this way. If I have a surface which is a closed surface like this, then the normal which is coming out from this surface, that normal is taken as a positive direction. So, while defining the unit normal for the surface, there is no specific notation. However, later on when we will try to connect the contours to the surface for an open surface, that time we will follow again the convention of the right hand rule, and then we will specifically choose the direction for the unit normal for the surface and the contours. So, in this case, let us say we can define, if volume was closed, if surface was closed, then we define the unit normal coming outwards. If the surface is open, then any direction can be taken as the direction of the unit normal. The third possibility we said is the volume integral. So, since we are now defining this quantity over the volume, we have some function which is a scalar quantity which is filling this volume. So, if I integrate the total scalar quantity over this volume, that gives me the volume integral. So, I have some volume here and I have some scalar quantity which is filling this volume, which is given by f. If I take a infinitesimally small volume in this, that volume is, let us say, given by dV, where V is the volume, then the integration over this will be a triple integration. So, we have here volume integral, which is the triple integral, this function f dV. So, essentially when we try to now relate the different integrations, the line integration to surface integration to the volume integration, essentially the vector fields first are operated by the operator del, and then there is a relationship between these del operated fields in the integration domain. So, there are two important theorems which essentially relate this, and they are called the divergence theorem and the Stokes theorem. So, we have a important theorem what is called the divergence theorem, which converts a surface integral for a vector field to a volume integral. So, if I have a vector field A, take vector field A, then the divergence theorem states that for a closed surface, for a closed surface, the integral A dot d A, that is equal to the volume integral of divergence of A. So, if I consider a surface, it has a total surface area, let us say, is given by S, and the total volume for this is V. If I take the surface integral of the vector A on the total surface S, then that is equal to the volume integral of the divergence of A over this volume. So, if you are having a vector and if you know the surface integral of this vector, the surface integral can be converted into a volume integral by operating this vector A with a del operator with a dot product. That means we take a divergence of vector A and take the volume integral of that, that is same as the surface integral of the vector A. This theorem is called the divergence theorem. So, whenever we have a need to convert from volume integral to surface integral or vice versa, this theorem comes very handy. The another theorem which is again important theorem, and that converts the surface integral into the line integral, and that theorem is called the Stokes theorem. So, if I have an open surface now, something like this, I have a contour for this surface. So, this is the contour C and I have this surface. So, I have some surface area S. So, the surface is open and the boundary of this surface is this contour C. Now, I can have a unit area here and that is the direction of, let us say, n, which is the unit vector for the area. Then I have this contour for which I have to define the direction of L, because when I do contour integration I will require L. So, essentially first we have to say how should I define this L with respect to n, and the convention is that if I again follow the right hand rule, if my contour goes like this, then it will be like this. So, the n will be coming inwards. If I take the contour which will be like this, then the n will be going outwards. So, if I take direction of the contour like this, that means the dl vector, if I define that way. So, if I take the contour positive direction like this, then the direction of the unit vector for the surface will be like that. If I change the direction of the contour integration in the opposite direction, the normal direction of the surface integral will be inwards. So, for this then we can write the contour is a closed contour in this case. So, the Stokes theorem states that over this contour C, the line integral of this vector A, you have a vector field again here which is A, that is equal to the surface integral, and in this case it is the open surface, curl of A dot dA. So, the line integral of this vector A on this contour is equal to the surface integral of the curl of this vector A. So, this theorem can be used now for converting the line integral to surface integral and vice versa. So, again summarizing this, if I have a closed surface, then the surface integral and the volume integral can be related by the divergence theorem, and if I have an open surface, then the line integral and the surface integral can be related through the Stokes theorem. So, later on for solving the problem of electromagnetics, especially when we write the Maxwell's equation in the integral and differential form, these two theorems become very important. They come very handy in converting from the differential to the integral form. Having understood this basics of the vectors, now we can go to the basic quantities of the electromagnetics, which we are going to make use of in the further analysis. That is the quantities like electric and magnetic fields. Well, the origin of the entire electromagnetic phenomena is the basic charge. So, if I consider a charge, we know from our basic Coulomb's law, this charge has an effect around it. So, if I put another charge in the vicinity of that, it experiences a force. This effect is measured by a quantity what is called the electric field. So, if I take a charge and go in the vicinity of that, I experience a force which is characterized by a quantity called electric field. However, if I keep this charge in motion, then it constitutes a current, because current is nothing but the rate of change of charge. So, if the charge starts moving, you have a sustained flow of charges that essentially gives you current, and then we have the magnetic fields. So, the same charge when it is static, stationary, it gives you the electric field. If it starts moving, then it gives you current, and that gives you the magnetic field. The charge get accelerated also. So, if you accelerate the charges, then it gives you the electric and magnetic fields both. So, essentially we are dealing with the quantities here, the charges, currents, electric and magnetic fields, and try to establish the relationship between these quantities. The relationship which we have between these quantities is given by what is called Maxwell's equations. So, essentially now starting with the basics of these quantities, we will try to establish the relationship between them from the laws of physics, and when we write these laws of physics in the mathematical form using the vector notation and the vector theorems which we have established, we get what is called the Maxwell's equation. So, the quantity which we have now is what is called, the first quantity is the electric field, E, which is nothing but the force experienced by unit charge. So, if I have some charge here, by Coulomb's law I will experience a force at a location in the vicinity of this charge. If I measure this force per unit charge, that quantity is what is called the electric field at that location. Since we are talking about the force per unit charge, the electric field is a vector quantity. So, it has a direction and it has its magnitude. The unit of electric field is volts per meter. So, electric field is given by volts per meter. Then we have a medium property, that if I measure the electric field in, let us say, vacuum, I will get certain force. If I measure the same thing and if I change the medium parameter to some other dielectric, then the force will change. So, the quantity which does not depend upon the medium parameters is the electric displacement vector. So, the electric field is a quantity which is related to the charge which is producing this field, but it also is related to the medium parameters, which is what is called the permittivity of the medium. So, we have a medium parameter called permittivity, which is denoted by epsilon, and it has a unit farad per meter. So, if the medium parameter changes, the permittivity of the medium changes, and because of that the electric field measured at that point changes. The permittivity of the vacuum or the free space is denoted by epsilon 0. So, for the free space, we have epsilon is equal to epsilon 0, and its value is approximately 1 over 36 pi into 10 to the power minus 9 farad per meter. So, in the space which is nothing, which is vacuum, even for that the permittivity has a value, and which is this. Many times this is also written as 8.86 10 to the power minus 12 and so on. However, it is easy to remember 1 upon 36 pi into 10 to the power minus 9 rather than remembering 8.8 something. So, generally we prefer to write the permittivity of the free space as 1 over 36 pi into 10 to the power minus 9 farads per meter. Then if we take another medium whose permittivity is some epsilon, the ratio of the epsilon to the epsilon 0 is what is called the dielectric constant or the relative permittivity of the medium. So, we have the dielectric constant epsilon r, also called as relative permittivity, that is equal to the permittivity of the medium divided by the permittivity of the free space, that is epsilon 0. Then the quantity which is independent of the medium parameters, that is what is called the electric displacement vector, that is the product of the electric field and the permittivity of the medium. So, we have a quantity electric displacement vector denoted by D, which is equal to permittivity of the medium multiplied by the electric field. So, when the medium property change, the epsilon changes, but the D remains same. D does not depend upon the medium properties, it depends upon actually the charge which is creating this field, irrespective of which medium it is creating this field. So, D remains same, it does not change from medium to medium. The quantity which changes is the electric field depending upon what is the permittivity of the medium. Now, this quantity epsilon in a general medium can be constant everywhere, can be uniform, or it can vary as a function of space in 3-dimensional space. It can also depend upon the direction. What that means is, if I measure the permittivity in certain direction, it has certain value. If I measure the permittivity in some other direction, it will have another value. So, in general, this quantity epsilon may be direction dependent, it may be space dependent. So, if epsilon varies as a function of space, then we call the medium as an inhomogeneous medium. So, epsilon varies with space, this gives you the inhomogeneous medium. If epsilon is a function of direction, if epsilon is direction dependent, then the medium is called an anisotropic medium. Isotropic medium. So, if epsilon varies as a function of space, we call the medium inhomogeneous. If the epsilon is direction dependent, then the medium is called anisotropic. If the medium is not varying as a function of space, then we call the medium homogeneous, and if epsilon is not varying as a function of direction, then we call that medium is isotropic medium. In this course, we deal with the media which are homogeneous and isotropic media. So, here we consider only homogeneous and isotropic media. What that means is that the dielectric constant of the medium or permittivity of the medium is neither direction dependent nor it is varying as a function of space. In general, however, if the medium was anisotropic, then this quantity epsilon is not a scalar quantity. In fact, it becomes a 3 by 3 matrix, and D is now equal to this 3 by 3 matrix epsilon multiplied by this E, which is a vector. So, for an anisotropic case, the epsilon is a 3 by 3 matrix, whereas if I take a medium which is isotropic, then epsilon is a scalar quantity. So, in this course, we essentially deal with the media for which epsilon or the dielectric constant is a scalar quantity. What that means is that in a homogeneous medium, if this epsilon is a scalar quantity, the D is nothing but a scaled version of E. So, if I compare D and E, they have different magnitude, these two vectors, but the direction of E and D are same. That means, in an isotropic medium, the displacement vector and the electric field, they are in the same direction. However, if I take a medium which is anisotropic, then in general this is a 3 by 3 matrix. So, essentially it rotates this vector E, and in general the displacement vector and the electric field vector are not in the same direction. So, we say that this is E and this is D, this is E. This will be the case if the medium is isotropic, whereas this will be the case if the medium is anisotropic. Because as we said, the displacement vector D is given in this case by a 3 by 3 matrix. So, let me just write that as epsilon xx, epsilon xy, epsilon xz, epsilon yx, epsilon yy, epsilon yz, epsilon zx, epsilon zy, epsilon zz, multiplied by this vector which is Ex, Ey, Ez. So, this is equal to 3 components of the vectors, this is dx, dy, dz. So, as you can see here, if I had a vector whose components are Ex, Ey, Ez, after transforming through this matrix which is the permittivity of the anisotropic medium, that will give me displacement vector which will not have the same direction of the electric field. So, I will have a situation something like that. Then we have a quantity which is useful, which we define, and that is the electric potential at a point in the field, and that is nothing but the negative gradient of the potential is the electric field. So, the electric field is related to the electric potential, is a scalar quantity V, and that is related to the electric field as the electric field is minus gradient of the voltage. So, if I know the potential at a point, then I can take the gradient of that, and that gives me the electric field at that location. From here the unit which we have got for the electric field essentially comes from this definition, that here we have defined the potential which is like that. The unit for the voltage is volts. The del operator is a differential, spatial differential operator, so it is d by dx, so its units are 1 by length or per meter. So that gives me the unit of the electric field which is volts per meter. So this relation for converting or from finding out the electric field from the potential, it turns out very handy whenever we try to find the electric field in a general complex distribution of the charges. If we calculate the electric field at a particular location, and if I find the electric field because of each component of the charges which are distributed in space, you have to carry out the vector additions at that point for the electric field. So generally it turns out to be easier to find out the potential at that point due to all the different charges. I can add those potential because these are scalar quantities, and then you find out the gradient of that will give the electric field. So these are the very basic qualities for representing the electrostatic parameters, the electric field and the electric potential. When we meet next time, then we will try to now establish the basic laws which connect the electric displacement and the charges which are responsible for creating the electric displacement, and then in subsequently the similar analysis we will carry out for the magnetic fields or the magnetic flux densities. So let us summarize what we did today. Today we saw some of the more vector operations. We saw two very important theorems for the vector integration, what is called the divergence and Stokes theorems, which convert the surface integral to volume integral and line integral to surface integrals. And then we also saw the basic relationship between the displacement vector and the electric field, and a parameter what is called the permittivity of the medium, and how it changes for isotropic medium to anisotropic medium.